Okay. Um, this lecture is about air vessel. This is our third lecture in reciprocating pump. We will discuss about air vessel in this lecture. Okay, air vessel is a closed chamber made up of cast iron, and it is used to provide a uniform discharge from a reciprocating pump, and it has an opening at its base. Water can enter the chamber and can flow out from the chamber, and the air is trapped above the water. Now, the air vessels are connected as nearly as possible to the cylinder in a reciprocating pump, which means the distance between this cylinder and the reciprocating pump will be very less compared to the length of the pipe, suction or delivery side. Now, why we need why we need an air vessel in reciprocating pump? See, consider delivery stroke. During the first half of the delivery stroke, that is from 0 to 90 degree, then the acceleration will be maximum at 0 and 0 at 90 degree. Then the water moves at a higher velocity than the mean velocity through the pipe. And similarly, during the other half of the stroke, that is from 90 degree to 180 degree, the piston retards, which means the mean velocity, the velocity with which the water leaves from the piston will be less than the mean velocity. So we will get an intermittent discharge of the fluid from the pump. This phenomenon or this non-uniform discharge can be reduced or eliminated by fitting air vessels at the suction and delivery pipe. So, the air vessel which stores the excess amount of water or fluid during the first half of the delivery stroke and release the excess water which stored in the air vessel during the first half of the delivery stroke in the second half of the delivery stroke when the velocity less than the mean velocity. Similarly, it supplies water in the first half of the suction stroke and it stores water during the second half of the suction stroke. This is done by the compressed air inside the air vessel. Now, if omega is the angular velocity of the crank, then the uniform flow rate or mean flow rate Q mean is equal to, it is LAN by 60. If you substitute n in terms of omega, you will get LA omega by 2 pi. Then you can calculate the mean velocity in both delivery and suction pipe using this equation, Q mean divided by area of pipe. Now discuss about what are the advantages when we fit an air vessel in a reciprocating pump. In suction side, the main advantages are: first one, cavitation may be avoided; second, higher speed of the pump can be achieved, and we can use higher length of the suction pipe. These are the three advantages of air vessel in suction side. In delivery side, we will get a uniform discharge, and the power requirement, if you fit an air vessel, will be less compared to a reciprocating pump without air vessel. In flow to or from the air vessel, see, we know that mean discharge or Q mean is equal to LA omega by 2 pi, and L is nothing but 2R, where R is the radius of crank. 2RA omega by 2 pi, that is then AR omega by pi we will get. Then mean velocity is equal to this Q, mean velocity of the fluid in the pipe, is equal to Q mean divided by area of pipe. So Q mean is A omega R by pi divided by A is equal to A omega R by A pi. And see, without an air vessel, we see that velocity of fluid through the pipe, velocity of fluid through the pipe is AR omega sin theta by A by A R omega sin theta, and the discharge from cylinder is equal to this velocity into area of pipe. So this area and this area A cancels, and we will get AR omega sin theta. The difference in this discharges determines whether the water flows into the vessel or from the vessel. If sin theta minus 1 by pi greater than 0, then water flows to the air vessel, that is QC is greater than Q mean. Q mean is the discharge through the pipe. QC is the discharge from the cylinder, if you consider delivery pipe. And if you consider suction pipe, QC is the water sucked to the cylinder, and Q mean is the discharge through the suction pipe. So if sin theta minus 1 by pi less than 0, then the water flows from the air vessel. And one more case is that is what happens if sin theta is equal to 1 by pi. If sin theta is equal to 1 by pi, then this becomes 0, that is there is no difference in flow rates. So there is no flow from the air vessel or into the air vessel. Now by fitting an air vessel to a reciprocating pump, we can save some work. So how do you find the work saved by using an air vessel? So that is the work done without an air vessel minus work done with the air vessel is the work saved. Okay. So work done during a stroke against friction without air vessel. Why we are taking only friction? That is important because here the velocity in suction and delivery pipe are uniform velocity, we mean. There is no change in acceleration. So the effect of acceleration will be very, very less. The variation will be only in this area and this area. So that we can neglect. That is why we are taking only friction. We know that the friction is the work done against friction is equal to rho GAN by 60 into L into 2 by 3 HF. Why this 2 by 3 HF? 2 by 3 HF because it's a parabolic in nature. The head loss due to friction is the curve is parabolic curve, where HF is equal to 4FL by 2 GD into V square. V is A by A into omega R the whole square. Now, work done during a stroke against friction with the air vessel, and if you fit an air vessel, then it will be rho g an by 60 into L into HF. See, area of indicator diagram now changes to area of a rectangle because see, due to fitting of air vessel, the head loss due to friction is independent of theta, and hence the indicator plot is a rectangle. That is, if you fit an air vessel, then the head loss due to friction is not a parabolic curve, it's a straight line. That is there is no effect, or the friction is independent of crank angle, so we can treat it as a straight line. This shaded area is the area, this is the head loss due to friction. So HF is equal to 4FL by 2 GD A by A into omega R by pi the whole square. Now work saved is equal to, if you want to show it in percentage, then work done WD1 minus WD2 divided by WD1 into 100. Okay. So this is all about air vessels. We will continue our problems or tutorials in next lecture. Thank you.